Okay, so in this video, we're going to talk a little bit about chemical formulas and some of the information we can learn from them. So, although we've been kind of looking at them, we've glanced at them, we kind of know what they tell us, let's get into some real detail about chemical formulas in this video. So with chemical formulas, we basically need a shorthand way to represent a chemical molecule, okay? So, again, we're using kind of that abstraction of a model where we can say we're not individually putting all those little teeny tiny atoms on our paper, right, to say, oh, this is CH4. We need a way to just represent chemical molecules, and we need a shorthand way to do that, and that way is through chemical formulas. So they're used to indicate that chemical composition. So when we're thinking about the law of constant composition, we're using chemical formulas to display that exhibition of the law of constant composition. So your chemical formula shows you the ratio of each type of atom contained within a compound. So it's going to show you what type of atoms there are and how many there are. And then we can kind of compare those to see how many there are compared to other kinds. So chemical formulas use the chemical symbol of an atom, and then they use a subscript, which is a number that hangs below the line. So when you're writing it, you could think that the line was at the bottom of the H and the O, and the two kind of intersects that. So it hangs below the line. It hangs below where we would usually write our numbers. So we could do that when we were writing by hand, or we can use the subscript feature when we're on the computer typing. And that's how we denote the number of each atom we have. So my goal here is that you should be able to look at a chemical formula and count the number of atoms in it by the end here. So you should be able to take any chemical formula I give you and determine the total number of atoms as well as how many of each type of atom you have. So on the screen we have the chemical formula for water, H2O. We kind of know that. Everybody knows it's H2O. So water is H2O. So why H2O, though? Well, water is made up of 2 hydrogen atoms and 1 oxygen atom. So our chemical formula is showing us that our water is made up of 2 hydrogen atoms and 1 oxygen atom. So the symbol for hydrogen is H, so it's written here first. And then it's got a subscript of 2. So that means we have 2 hydrogen atoms. And then over here we have oxygen, and oxygen has that chemical symbol O. However, we don't see a subscript. We don't see any extra number below the line or anything here with the O. So we assume that means it's 1. So here I have 2 hydrogens and 1 oxygen atom. So that's the idea when we look at chemical formulas. So we should be able to look at a chemical formula and determine all of those atoms in the chemical formula. Okay, so before we move on to some examples, I want to give you some warnings about what happens when we write chemical formulas and some things about chemical formulas, okay? So you have got to be sure you're using the correct chemical symbol. So you have a periodic table, you'll always have your periodic table to triple check. So if you mean selenium, you're using Se. If you mean silicon, you're using Si. If you mean sulfur, you're using S, okay? If you get those mixed up, I don't know what you mean. I'm not going to be able to assume you meant the other chemical formula. You're probably not going to get your answer right, okay? So keep in mind, if you use the wrong chemical symbol, you're talking about the wrong chemical. So it's just wrong. So if you use the wrong chemical symbol, I may count your answer wrong because you're talking about the wrong compound, therefore. And the other big to-do with chemical formulas are the subscripts. So here's the deal. Your subscripts have got to be properly formatted unless I say otherwise. So if you are able to format subscripts, it must be done. So if you are writing by hand, you must always use a subscript because you can always write subscripts by hand. You will make your letters or your numbers hang below the line of your letters, okay? If you write them as full-fledged letters, it's going to be wrong because I don't know what you mean. H with a full number 2 next to it means something entirely different than H subscript 2. You have to be sure you're saying what you mean in chemistry. So Hypothetically, there might be situations in the future in Canvas where I might ask you to type your answer without them, but the only time you are excused from using proper subscripts is if I explicitly say that. So I will literally write the words, you do not have to use subscripts if you do not have to use them. Otherwise, you will always have to use them. I do my best to format your homework so that it's very clear whether or not you need to use subscripts. And I also include information about how to use subscripts in Canvas as well in your homework. So you gotta format your subscripts or it might be wrong, okay? Keep that in mind as we move forward. All right, so let's do some pretty easy examples of our counting atoms in chemical formulas. So if I'm looking at that first formula there, CO2, that's carbon dioxide, the gas that we breathe out after we do respiration. So after we breathe oxygen in and we breathe out, we're making carbon dioxide. So we want to figure out how many carbon atoms we have in our carbon dioxide molecule. So if I'm looking at this chemical formula, I see the capital C standing for carbon, so I'm going to look at that atom, and I can see that it's missing a subscript, aka it has a subscript of 1. So if I look at this chemical formula for carbon dioxide, I can see that I have 1 carbon atom. If I look at that same chemical formula, I see, and I want to know how many oxygen atoms I have, I can check that out, and I see, okay, I've got the chemical symbol for C, not oxygen, don't care about it. I want to know how many oxygen atoms. Hey, I've got the chemical symbol O, that stands for oxygen, that's the one I want, and it has a subscript of 2, so I must have 2 oxygen atoms. Okay, so 1 carbon atom and 2 oxygen atoms. So if I want to know how many total atoms there are in the chemical formula CO2, I would look at this and I would say, okay, I see 1 chemical symbol here with no subscript, which means I have 1 of those, so I have 1 carbon atom. And I see the chemical symbol O for oxygen, and it has a subscript of 2, so that must mean I have 2 oxygen atoms. So there must be 3 total atoms in my carbon dioxide molecule. So all you got to do is look at the subscript to determine how many of each type of atom you have, and then from there, you should be able to count the total number of all the atoms. So I've got 2 more on the screen here to practice with. So how many carbon atoms are in the C6H12O6 molecule? C6H12O6 is actually a very sweet molecule. It's sugar. So C6H12O6 is sugar. So we want to know how many carbon atoms in our sugar molecule. So we see that C for carbon right there up front. We see that it has a subscript of 6, which means we have 6 carbon atoms. If we want to know how many hydrogen atoms we have, we look for that H symbol. We see, okay, we've got H with a subscript of 12, H sub 12. We see that we have 12 hydrogen atoms. And then when we look here at the oxygen, oxygen has that chemical symbol of O, and we see that we have 6 oxygen atoms here. So 6 carbon atoms, 12 hydrogen atoms, 6 oxygen atoms. And then overall, if we add all of that up, we have 24 atoms in our molecule. So 24 atoms in our molecule total. I should have put the total there on the screen for you. So 24 atoms total in our molecule, 6 of which are carbon, 12 of which are hydrogen, and 6 of which are oxygen. So I put 1 more molecule up here on your screen for you. So this is C4H10. So that's actually butane. That's one of the fuels we often use. It's a carbon-based gas. So butane is there. So that would be C4H10, okay? So we want to figure out how many carbon and hydrogen atoms we have, as well as how many total. So if I'm looking for how many carbon atoms I have, I see very first and foremost, I have that chemical symbol of C. So that means I have carbon here, and I look to the subscript to know how many carbon atoms I have. So I've got 4 carbon atoms since there is a subscript of 4. If I want to know how many hydrogen atoms I have, I look for that H for the chemical symbol of hydrogen. And if I have that chemical symbol for H of hydrogen and it has a subscript after it of 10, H sub 10, H10, that's going to be 10 hydrogen atoms. So if I want to know how many atoms there are total in butane, there would be 14 atoms total, 4 carbon atoms and 10 hydrogen atoms. So 14 total atoms. There's my total atoms. So that would be kind of how you can count these and figure these out along your way. So if I give you a chemical formula, you should be able to easily look at it and determine how many atoms of each kind, as well as how many total atoms there are in a chemical formula. So the thing that becomes interesting with chemical formulas are what we call polyatomic ions, okay? So sometimes we might have these clusters of atoms that come together to form an ion, just like elements can form ions, okay? So if we think about it, if we take an atom and it gains or loses electrons, we have an imbalance of positive and negative charges, therefore, so we have an ion. In this case, when the atoms come together, they bond together to make this polyatomic ion. They have an imbalance of protons total versus electrons total in all of the atoms, so they form an ion. Same concept. So we call these polyatomic ions, okay? Why polyatomic? Well, poly means many, atomic meaning atoms, and ion meaning, again, a charged particle. So a many-atomed charged particle. Before, we were looking at monatomic ions. So mon meaning one, atomic meaning atoms again. So we had monatomic, one atom ions. Now we're looking at many atomed ions, okay? So you'll start to be able to recognize polyatomic ions when we look at our chemical formulas as we go on throughout the semester. And we're going to talk about which ones exactly you need to actually know. The book has a longer list than I personally require. So you'll start to recognize them as we go along. However, it's good to put them in your back pocket and start to memorize and recognize them now. So they're going to do some really cool chemistry as we continue to talk about compounds. However, for now, you just kind of need to know that they combine to form this ion and they have a chemical formula that represents themselves. And when we look at a chemical formula and we want to have more than one copy of our polyatomic ion, like before we have H2O, it's got 2 H atoms. Let's say we want to have 2 copies of our polyatomic ion. We're going to use parentheses to do that. So if you see parentheses in a chemical formula, that is a huge tip that you have a polyatomic ion. So what in the heck do I mean? These are some common polyatomic ions that you will need to know. So you need to know these down pat. You need to know them by the name, by the ion formula, as well as know their charge, okay? So you got to know those 3 things about the polyatomic ions you see on your screen right now, okay? So that being said, you can kind of check them out here. The first one we see on the screen is acetate. So acetate is made up of C2H3O2, so 2 carbon atoms, 3 hydrogen atoms, and 2 oxygen atoms. When all of those combine together, we find that we have an extra electron, so it has a 1 negative charge. So it has 1 extra negative there. It's got a 1 negative charge overall. So anytime you see this grouping C2H3O2, you know that it has a negative charge, and it is a polyatomic ion. So again, check out these guys on your screen, become familiar with them. We're gonna use them a ton in this chapter and we'll continue to use them. So it's kind of one of those things where it's like as you continue to use it, that's really where the memory comes from, is because you're using it all the time. You should start to know them now. You're gonna have to know them by heart by the exam. However, I think we're gonna use them a ton, so don't stress too much. You'll see them often. However, there is one really interesting polyatomic ion on our screen I want to point out for you right now, and that is ammonium. So I've highlighted ammonium in yellow on your screen specifically because it has a positive charge. It is our only cation that is a polyatomic ion. Remember, cations are positively charged ions. Cations are positive, and anions are negatively charged ions. So these words still apply here. So this is a negatively charged ion, phosphate is. So phosphate is an anion. So we have a ton of anions on the screen here and one cation highlighted here in yellow. So ammonium is a cation, and it's NH4+. So you may hear ammonium and think ammonia. Well, ammonia is NH3, and ammonium is NH4+, because that hydrogen adding an extra one on is going to make it a positive. You're going to have an extra proton. So that's the difference between ammonia and ammonium. So ammonium is actually the ion version versus ammonia is the regular version that has no charge. The net charge is 0. The neutral atom would be, or the neutral molecule would be ammonia, and the ion is ammonium, okay? So it's interesting that this is the one positively charged one, and it's going to stand out as we start to talk about ionic compounds. So you should be familiar with all of them, but ammonia is kind of ammonium is kind of a special case of polyatomic ions. So check that guy out. So I was talking a little bit before about parentheses with polyatomic ions, okay? So if we want to look at a polyatomic ion and we're including it in a larger molecule where it's a part of something bigger, so we're not just looking at the chemical formula of the polyatomic ion itself as we were doing on the last screen. Here we're looking at what does it look like if we put a polyatomic ion into a chemical formula, okay? So let's check out what's on the screen so we can see what we've got going on, all right? So here we're looking at the chemical formula for magnesium nitrate. So we can see we have the chemical symbol for magnesium here. We've got the symbol for that NO3 group. We've got that chemical formula, that ion formula of the polyatomic ion nitrate here. So let's break down this chemical formula so we can determine what we got going on. So first and foremost, of course, that magnesium atom, Mg, right there in the front. I know Mg is the chemical formula or chemical symbol for magnesium. And then I don't see a subscript after it. So if I don't see a subscript, I assume the subscript is 1. So therefore, I have one magnesium atom in this chemical formula. However, I have something interesting happening here with the parentheses around my polyatomic ion, okay? So I see that in here, I have that NO3 ion, okay? I see that I've got NO3 in the parentheses. So nitrogen does not have a subscript, so therefore we assume that it is 1. So I've got one nitrogen atom, and then here I've got the chemical symbol O for oxygen with a subscript of 3. So therefore, I must have 3 oxygen atoms. So every single nitrate is always made up of 1 nitrogen and 3 oxygens, okay? However, in this case, what the parentheses all the way around the NO3 with a subscript of 2 here at the end means is that I have 2 entire copies of that nitrate ion, okay? So what we're saying is that we have 1 magnesium ion and we have 2 nitrate ions. So if I want to say I've got 2 entire copies of my nitrate, I use parentheses around the chemical symbol of nitrate so that I can say that I want 2 whole copies of the whole thing. So this is saying that I have 2 nitrate ions. So what might this look like? So this might look like this. So I might have a magnesium ion. We know magnesium takes on a charge of 2+, so I might have a magnesium ion. And then what it's telling me is I have 2 NO3 groups. So this is kind of how we can consider it to look. Forgive me while I'm being bad at drawing circles. So this might be how it would look for us. So what that's saying is that we have 2 whole NO3 groups with our 1 magnesium ion. So the subscript 2 with the parentheses tells us that we have these 2 NO3 groups. So that means I have 2 entire copies of my nitrate ion, okay? So if I want to determine how many nitrogen atoms are in this chemical formula, I would have to think about the fact that I have 2 whole copies of nitrate. So that must mean I have 2 nitrogen atoms because I've got 1 from 1 copy of nitrate and I've got another from the second copy of nitrate, okay? So if I'm looking at this subscript 2 applies to everything that's in here. So you could kind of almost even consider it a multiplication if you don't want to think about the copies, okay? So you might think of it as all these copies of NO3. Or if you want to do something a little bit more quickly, or if you're more mathy kind of styled, you might think, okay, nitrogen has an implied subscript of 1, so I think of nitrogen as having a subscript of 1, so I've got 2 times 1 nitrogen atoms, okay? 2 nitrogen atoms. Well, I have O subscript 3. I might think, okay, you know, I've got 2 copies of my nitrogen, or my nitrate. I've got 2 copies of my nitrate. So that must mean I've got 1 group with 3 oxygens. I've got another group with 3 oxygens, so I must have 6 total. Or again, you might think of it as 3 oxygens times 2 copies. So 3 times 2, 6 oxygens, okay? So that's kind of the information that's contained here in our chemical formula. So if we want to increase the number of copies of polyatomic ions we have to use parentheses around the whole thing with a subscript, okay? So because these parentheses are here, we also know that that 2 does not apply to the magnesium either. It's outside the parentheses. 2 doesn't apply. The 2 only applies to what's in the parentheses directly in front of it. So let's do some examples of counting the number of atoms when we're looking at having polyatomic ions, okay? So we want to count the total number of each kind of atom as well as the total number of atoms in this chemical formula. That chemical formula is calcium hydroxide. So when you see hydroxide, that likely means you have a base. So we'll talk about acids and bases later, but here is a base on your screen for you, calcium hydroxide. So first and foremost, we want to know how many calcium, oxygen, and hydrogen atoms we have in there. So I'll start from left to right. I see that I've got calcium written here first. So calcium does not have a subscript after it, and it's outside of the parentheses, so that 2 doesn't apply to it. So it looks like my calcium has a subscript of just 1, so therefore I have 1 calcium atom, okay? If I want to know how many oxygen atoms I have as I'm moving across, I have to think about the fact that if I look at my parentheses, my oxygen is inside the parentheses that tell me I have 2 whole copies of the hydroxide ion. So if each hydroxide has 1 oxygen, and I have 2 hydroxides, I must have 2 oxygens. So 2 oxygen atoms, 1 calcium atom. And then I want to know how many hydrogen atoms as well. Same thing. Well, hydrogen's inside the parentheses. It has a subscript of 1. It has a subscript of 2 outside the parentheses, so I must have 2 hydrogen atoms. So 1 calcium atom, 2 oxygen atoms, 2 hydrogen atoms. If I add all that up, I must have 5 total atoms. So 1 calcium atom, 2 oxygen atoms, 2 hydrogen atoms, 5 total atoms. Pretty straightforward. You just got to remember what the parentheses mean. However, if we look at our next example, Na2SO4, we don't see any parentheses. Okay, so it's a little bit trickier right off the bat. We don't necessarily see right away that we have something weird going on. However, when we see those SO4 together, when we see that grouping, we know we have a sulfate ion, okay? So we've got a sulfate polyatomic ion. So if we only have 1 copy of the polyatomic ion in any case, we do not use parentheses. So when you're writing chemical formulas, not only do you have to worry about using the correct chemical symbol, not only do you have to worry about properly writing subscripts, You just got to make sure when you're writing chemical formulas with polyatomic ions in them, you're using parentheses correctly, or you're leaving out the parentheses if they're not meant to be there, okay? So that's why there's no parentheses around the SO4, is because we only have one copy of SO4. It's kind of like having a subscript of 1 is writing the polyatomic ion without any parentheses. So we don't write the subscript of 1, so we don't write the parentheses either. That's kind of what's happening here. So we have a sulfate and we have some sodium. So we've got sodium sulfate here. So if I want to know how many kinds of each atom, I'm going to work left to right and we'll count them up. So first thing I see here is sodium. I look at the sodium. Sodium has a subscript of 2. I must have 2 sodium atoms, okay? Next thing I see is I have sulfur. There are no parentheses. There's nothing else. I want to know how many sulfur atoms I have. I have 1 sulfur atom. It does not have a subscript, no parentheses. No subscript means you only have 1. It's an implied subscript of 1. And then the next thing I see is an O, the chemical symbol again for oxygen. So I see that I have 4 total oxygen atoms because I've got a subscript of 4 on the O. I don't see any parentheses. I don't see anything else. So I know I just have 4 oxygen atoms, okay? So if I have 2 sodium atoms, I have 1 sulfur atom, and I have 4 oxygen atoms, I have 7 total atoms in my molecule. So you should be able to look at a chemical formula regardless of whether or not it has a polyatomic ion in it, and you should therefore be able to count the number of each atom and then total them up to get the total number of atoms in a chemical formula.